This is Moby, a self-published author. He purchased a half-calf caramel macchiato at a local coffee shop. But after writing about the rich history of the rubber band for just a few hours, his drink was ice cold. The cafe wouldn't refund his money, and now he's suing. This is Tim, the cafe's barista. He says the customer is always wrong. Plus some know-it-all stuff about physics and molecules. What you are about to witness is real. The participants are not actors, they are actual litigants. Both parties have agreed to have their case settled here, before Judge Marilyn Mainframe, in our forum, the People's Court.
Your Honor, I'd like to admit this letter into evidence, just as soon as I read it. Dear Tim and Moby, how does a thermos keep my soup from getting cold? Thanks, Mrs. Nichols' class. Now, Your Honor, Mrs. Nichols' class brings up an interesting point. Because, as we've all noticed, hot things don't stay hot. Once soup or cocoa or single-origin fair trade coffee comes off the stove, it starts to get colder. And it'll keep cooling off until it's the same temperature as the room. Cold drinks do the opposite. They'll keep warming up until they reach the temperature of their surroundings. Yes, putting a cold drink in a thermos will slow the warming. Or the cooling, if we're talking about a hot drink. So, the plaintiff's foofy espresso drink would stay hot longer, but not forever. Wait long enough, and that macchiato will be room temperature. Thermoses work because they minimize heat transfer. Heat always flows from warmer objects to cooler ones. And the greater the difference in temperature, the faster it'll happen. The only way to keep some coffee from cooling is to put it somewhere just as hot. Is the plaintiff suggesting I heat my establishment to 140 degrees? Because I really must point out 140 is the only proper temperature for a macchiato, or for... Sorry, Your Honor. I get a little carried away. Now, we've established that heat's always on the move, from warmer to cooler objects, and that a thermos can slow this process down. But to understand why, we need to get closer, a lot closer. Coffee, like any other substance, is made of tiny particles called molecules, and they're constantly jiggling and bumping into each other. In other words, they have kinetic energy, the energy of motion. Of course, we can't see any of this microscopic action, but we can feel it in the form of temperature. That's the average kinetic energy of all the molecules in an object. The warmer something feels, the faster its molecules are moving. I'm getting to the point, Your Honor, I promise. Because all of this microscopic motion is what makes heat transfer happen. First, through conduction, the transfer of kinetic energy by direct contact. When you hold a cup of coffee, your hands get warm. That's because molecules in the hot cup are slamming into molecules in your cooler hands. This is conduction. With each collision, the faster molecule slows down, and the slower one speeds up. Multiply that by a bazillion molecules, and you can guess what happens. Your hands, and the air all around the cup, absorb energy from the hot coffee, sucking away its molecular speed, which we read as a drop in temperature. But what if there weren't so many molecules around to bump into? That's one way thermoses minimize heat transfer. They're basically a bottle inside another bottle with empty space in between. It's a vacuum, a space with no molecules in it. So there's nothing there for the molecules in that hot bottle to bump into. Heat loss through conduction happens only at the very top of the bottle, where it's attached to the outer container. Well, there is one type of heat transfer that can go through a vacuum. It's called radiation. It also comes from the movement of particles, but on an even smaller scale. Molecules are made up of atoms, which you've probably seen drawn like this. Those little dots orbiting the center are electrons. When atoms are energized, like when they're heated up, electrons absorb some of that energy, but they don't hang on to it for long. They release the energy as a form of invisible light known as radiation. Molecules that absorb this radiation move faster, same as they would through conduction. That's why the inside of thermoses are often made of shiny substances. Since radiation is a kind of light, these materials reflect a lot of it back inside. Sorry, Judge, just a third and final type of heat transfer to cover. It's called convection, and it happens when a substance is unevenly heated. In convection, heat is transferred by molecules traveling from one place to another instead of just jiggling back and forth. That's why convection only happens in liquids and gases. They're called fluids because they have no fixed shape and flow easily. Heating water on a stove is a good example. The molecules at the bottom speed up, creating more space around themselves. This liquid becomes less dense or tightly packed, making it lighter than the liquid above it. So it rises through the heavier stuff away from the heat source. But then it cools down, becoming denser, so it sinks again. Warmer liquid rises and displaces the colder liquid at the top. This flow of material is called a convection current. This vintage coffee percolator works on the principle of convection, and it makes a wonderfully balanced cup of rendering a decision, but I was going to froth some oat milk for my closing argument. One free half-calf caramel macchiato in a thermos.